Hi, my name is Murthy Upmaka. I'm a field solutions engineer for Keysight Technologies. In this third video, which is the phased array fundamental feature series, we are going to discuss the effect of unequal interconnects between the parts in various channels. Let us take a simple building block from which we can build large phased arrays. The building block is a beamformer IC, something like from Analog Devices ADAR 1000. This is a 4-channel transceiver that can be connected to 4 antenna elements through 4 switches. These switches will switch between transmitter to the receiver, depending on the operation of the phased array. Now, as you can see, the transmission lines connecting from the chip to the switch are not equal. This may happen for any channel between any parts. And in fact, it will happen because we are trying to optimize the real estate on the PC board. So some transmission lines will have to go through different layers, and then some transmission lines have to go through VS, and some transmission lines can be joined directly. So there are all different, they all carry different S parameter characteristics. The point here is, how do we model these unequal transmission lines, interconnects in a phased array? We have array parts that already do for the case of unequal phase shifts, unequal attenuations, unequal amplifiers in each one of the channel. But we don't have a model that can model the unequal transmission lines. But fortunately, we can make use of either the phase shifter or the array attenuator parts shown here, since these parts actually work with the measured S parameter files for each of the states. For example, in the case of the array attenuator, the middle part, if we say it is a 4-bit attenuator, then there will be 2 to the power of 4, which is 16, attenuation states. If we say attenuation states are quantized to 1 dB value, then if the user provides a custom window of attenuation values, all these will be quantized to the quantization value specified in the step size. Further, if we make use of the measured S parameters as a function of frequency for each one of these attenuation states, then based on the values that we provide for the custom attenuation values, we can have the attenuator pick up the corresponding S parameter file. We use this trick to pick up the transmission line models if there are 16 16 channel phased array or 32 channel phased array, it doesn't matter. If we have, then as we compute the attenuation values for each one of the channels, those attenuation values, if we compute them to be sequential, or if we just specify them to be sequential, say 0, -1, -2, -15 dB for a 16 element array, then what happens is it will quantize. If we already specified quantized values, the quantization effect is essentially the same, picking our values. And Each one of these attenuation values, 0, -1, -2, etc., -6, -15, will correspond to 1, 2, 3, 4, up to 15 states, 16 states. So once the attenuator is able to pick up the particular state, the S parameter file corresponding to that attenuator can be made to pick up. That's what we do in the example here. We specify the attenuation values so that they go sequentially from 0 to -15. And the quantization is, we already specified the quantization value. So this has no effect. It will pick up the states, and those states will pick up the corresponding S parameter file. And then the S parameter file is a function of frequency. So knowing the frequency of operation of the phased array, it picks up all the four values of the S parameters at that frequency and applies it to the signal. So it will apply the mismatch loss, it will apply the insertion loss, it will apply the insertion phase, etc. So the trick is specifying sequentially. Now, there is one more detail here. We need to specify the attenuation values as a voltage ratios rather than power ratios. So we have to do this particular operation that will give the array of voltage ratios that we put in here. Now, as the attenuator, if we want a particular Taylor series or something like that, then if we put those values, they will be picked up appropriately. Um, but we don't need, we are not looking for a windowing, right? We are not looking for a operation as an attenuator. We are looking for as a transmission line picker rather than attenuation values. So the transmission line picker is the transmission line file picker is what happens when you specify sequentially here. Now, how do we apply this to a simulation? Let's take a simple phased array simulation. Ignore this second phase shifter for the time being. So if we want to form a beam in a particular direction, say 0, 0 in the bore site, then this phase shifter will compute the required phase shifts at the antenna elements so that the beam is formed in the bore site. But since the phase shifter has to connect to the antenna through interconnects, or we can call feed lines, these feed lines will all be unequal. Could be unequal, mostly they are unequal. So we have to account for them. So using the technique above, use a array attenuator to pick up the S parameter files 1, 2, 3 up to 16 as shown before. The S parameter files, as you have seen before, are organized in a properly indexed fashion. There is good description of the indexing in the help file of the system view phased array design kit. So what happens is the channel 1 will pick up the transmission line 1, channel 2, transmission line 2, etc. And that will disturb the phase shifts calculated by the phase shifter at the antenna array. So we get a beam that is not going to be in the 0, 0 direction, depending on how much these transmission lines are not equal and then how much they disturb the phase distribution. Here we are neglecting the differences in insertion losses. Actually, they are very negligible, so we can neglect. But in case your transmission line differences are also differ in attenuation, so we have to put a attenuator as well to calibrate out. Right now, we put only a phase shifter to calibrate out. So if we know the insertion phases of each one of these transmission lines, we can put those values, call them as calibrating phases, subtract them to preserve the phase distribution computed by this beam-forming phase shifter at the antenna array. That is what we have done in an example here. Initially, the feed lines are equal. So we get the direction of the beam as desired by us. Then we deployed unequal feed lines, which disturbed the phase distribution and then pointed the beam in a different direction. In order to preserve the beam back to the desired direction, we put another phase shifter and calibrated out the differences of the phases between the transmission lines in each one of these channels that preserved the beam directly back into the direction which is what we wanted. I hope you enjoyed this video. Thank you very much for watching.